Hi everyone, my name is Mina and I'm going to talk about a correlation clustering algorithm called Pruned Pivot that works for dynamic, parallel, and local computation models. This is a joint work with Kostia from Northwestern University and Slobodan from UC Davis. Okay, so let's first define the problem. Correlation clustering, as input, it gets an object and also a similarity function f that for every pair of objects tells us if they are similar or dissimilar. For example, here, these are our objects. The green solid lines indicate similarity. The red dashed lines indicate dissimilarity. And this, basically, we have this for every pair of objects. So this should have been a complete graph, but for simplicity, I haven't put all the edges here. Now, the goal in correlation clustering is to come up with a clustering that aligns with F as much as possible. So the cost is the disagreement between F and the clustering. For example, here, this disagreement is 3. 2 of this cost comes from the similar edges. For example, here we have one dissimilar edge that doesn't agree with the clustering. It is inside a cluster. Here's another one. And then we have a similar edge that disagrees with the clustering. It is between 2 clusters. So we basically want to minimize this cost. Correlation clustering has a lot of applications. I'll give you 2 examples. The first one is in aggregating accounts. So, for example, each person has accounts in different platforms. For example, in Netflix, Amazon, Gmail, etc. And think about this task where we want to aggregate accounts of each person. Correlation clustering can help with that. Another example is in semi-supervised learning. Imagine that these objects are Amazon items, and we don't have labels for each items. We have labels for some of them. We do correlation clustering, and then at the end, for example, we know that these 2 items are shoes. This tells us that, okay, these 2 items that are in the same cluster, they're shoes or shoe related. Okay. So there has been a lot of work done on correlation clustering. I couldn't list all of the ones that have been done in like the last 5 years on a single page. So this is not a complete list. But to just name a few, this problem was introduced by Bansal, Blum, and Chola in 2002-2004. It is a hard problem. It is APX hard. There is the weighted version of it, where each edge also has a weight, which indicates the degree of similarity or dissimilarity between the endpoints. But we're only focusing on the unweighted case, which I defined in the previous slide. There is this elegant and nice algorithm called Pivot that gives a 3 approximation algorithm. And it is the basis for a lot of algorithms in different settings. And also our algorithm is based off of this algorithm. But it doesn't give the best approximation factor. The best approximation factor is right now 1.437. The lower bound for the approximation factor right now is 1.042. So there's still a gap here. So this is a general setting for correlation clustering, but our work focuses on massive and dynamic graphs. You probably don't have a lot of convincing that why we're looking at massive graphs. These days, we deal with really big data sets. Our data centers are huge. And to give you a picture of how big they are, the world's biggest data center is bigger than the world's biggest airplane factory. So the world's biggest data center is 10.7 million square feet. It's in China. The world's biggest airplane factory is the Boeing factory, 4.2 million square feet. Okay, so we're dealing with a lot of data. 3 models of computation that abstract these massive and dynamic data sets are massively parallel computation, local computation algorithms, and dynamic algorithms. And I'm going to define each on a very high level. Okay, so let's first define MPC. If you're familiar with any of these platforms like MapReduce, MPC is the theoretical abstraction of these platforms. Otherwise, if you are not familiar with those, think of it this way, that we have a lot of different machines. Each machine has limited memory, but a lot of computation power. And these machines can talk to each other. And they communicate via an all-to-all synchronous round communication. And the goal here is to do the task at hand, whatever it is, in as few communication rounds as possible. So the measurement of the goodness of an MPC algorithm is the number of communication rounds. Okay. In LCA, the idea is that we have a huge input and we do some task on it. We indicate it by F, and the output is also huge. So the goal is to answer queries about part of the output by examining only a small portion of the input. The measure of goodness here is the number of probes, which is a proxy for this small portion of the input. Okay, so the smaller the number of probes are, the better the algorithm, the more efficient the algorithm is. And finally, in dynamic algorithms, the input data is changing. That's the idea. For example, here, these two edges change from being similar to dissimilar. And as a result, if we want to update this clustering, we have to put this object in a singleton. Okay. So the goal is to basically update the clustering as fast as possible. The measurement is update time per single edge change. Okay. So now that we know all of these different models, let's see what has been done. So this is the state of the art as of 2 years ago. The first algorithm is a constant factor approximation algorithm for the MPC model. The constant factor is quite big. It's around 700. And the round complexity is order 1, Spiko and et al. Then Behnajad et al. Came up with this algorithm that that can be adapted to all 3 models. It gives a 3 plus epsilon approximation factor. In MPC, it gives an order 1 over epsilon round complexity. In the local model, it gives delta to the order 1 over epsilon probes. Delta is the largest degree in the graph. In the dynamic setting, it gives a polylog n update time, where n is the number of nodes. Okay. So what we do is that we, similar to Behnajad et al., we give an algorithm that is adaptable to all 3 models. It also gives a 3 plus epsilon approximation. And in the MPC model, it gives an order log 1 over epsilon round. In LCA, it gives order delta over epsilon probes, and in dynamic, it works in order 1 over epsilon update time, so no dependency on n. Okay. Since correlation clustering is a really hot topic, there has been a lot of concurrent work to us. Mainly, there's this work by Kwan et al. That appeared in Stock 2024. Which they basically beat our MPC algorithm, both in approximation factor and in the round complexity. They give a 1.847 approximation algorithm in constant rounds. Okay. As far as we know, their algorithm doesn't adapt to the local setting, so our local algorithm is still the best. In the dynamic setting, there is this recent paper by Behnajad et al. They break this 3 approximation barrier, so they give a 2.997 approximation in polylog and update time. So their update time guarantee is still polylog n, not constant, but they beat the approximation factor. Okay. And in ICML 2024, there's this other paper for the dynamic setting, but where nodes are appearing and disappearing instead of edges changing. And obviously, this is a harder problem than when just one edge changes. So they give an order 1 approximation algorithm in polylog and update time. The order 1 it's quite big. It's a lot bigger than 3. But this is basically the best that we know for the node dynamic setting. Okay. So all of the algorithms that with approximation factor around 3, they are all coming from pivot. They are all modifications of pivot. So let's first see very roughly what pivot does. Before getting into that, slight change of notations. So we said that in correlation clustering, we're dealing with complete graphs with edges being labeled as similar or dissimilar. Now, instead of showing all the edges, we just showed the similar edges. So if two nodes are adjacent, they are similar. If they're not adjacent, they're dissimilar. Okay. Now, I'm not going to define pivot, but just gonna in a very high level say what it does. It's still a very simple algorithm. So what it does is that it first gives random ordering to the nodes, and then the cluster of each node is indicated by the cluster of its neighbors that have a lower number than it. So for example, here the clustering of 9 is indicated by the clustering of 4, 7, and 8. These are its neighbors that have a lower ordering number than 9. Clustering of 4 is indicated by 1 and 2. Okay, and if we want to know what cluster 11 has, we essentially need to know the cluster of all of these nodes. So pivot is very sequential, and you can also think of it as like a recursive algorithm. So if we want to know the clustering of 11, we need to first know the clustering of 6, 9, and 10, and then 4, 7, 8, etc. So we can think of it as a recursive algorithm. And so this is kind of the recursion tree for 11. And this recursion tree has a depth and a width. And for the width, you can think of it as basically how many neighbors each node has to look at. For example, here, basically the width is 3. So in order to make this process more efficient, there are 2 ideas that have been implemented in past work. For example, the first one is to limit the width. So for example, instead of looking at all of the neighbors of each node that has a smaller rank, we just look at a limited number of them. For example, we just look at 2 of them. So for example, for 9, we just look at 4 and 7. For 11, we just look at 6 and 9. We don't look at 10 anymore. And if when we are looking at the neighbors, when we are done basically with a number of nodes we can look at, we still don't know what cluster 11 should be, then we just put it in a singleton cluster, okay? The other idea is that we can limit the depth. So we basically limit the depth of our recursion tree. And again, if by that point, by the point that we've done all of our processing, we still don't know what cluster that node should go, then we just put that node in a singleton. Okay. These are all very abstract because I didn't explain pivot, but once you know what basically pivot does, these all become clear. But essentially, the high-level ideas are just to limit width and limit depth, and the implementation of these ideas is very simple. The challenge in both of these 2 papers is in analyzing the algorithm and showing that it still gives an almost 3 approximation. So our idea is basically to do both, limit the width and limit the depth. And again, the implementation of this algorithm is quite easy. And the challenge for us was basically to analyze the algorithm, because the analysis of these 2 previous algorithms, they are both very involved and both very different. So we couldn't just plug in their analysis, and we had to come up with new ways to analyze this algorithm. Okay, so to recap, we developed an algorithm called Pruned Pivot that can be implemented in MPCLC and in dynamic models. And our algorithm gives improvements in LCA and dynamic models. And as I said, in MPC, our algorithm was beat by this recent work. Okay. Now, for open questions, basically nothing is hiding correlation clustering. There's a lot of things to do still there. In the general setting, the approximation, there's a gap in the approximation factor in each of these settings. We don't know what the best approximation is. Probably it's not 3. It can be made better. So there's tons to do. And thank you for listening to my talk.